99% of developers don't get the Poisson distribution. If you were like me, discrete math was one of those non-core computer science classes that you had to take in first or second year that you absolutely hated. But the more I learned, the more I started to see the beauty of it all. If you're French, you might know that poisson means fish, so you'd expect this concept in probability theory and statistics to be related to the mass distribution of fish, like salmon or Atlantic cod. But no, you're actually wrong. Poisson distribution is one of those concepts like Lagrange multipliers, Jacobian matrices, or Taylor series that you may have heard of in passing, or may have come across in a lecture, but that you simply have zero recollection of. And that may be a problem, right? You should take the time to at least understand some of these core math principles, because although you don't need to know math, you should take the time to at least understand some of these core math principles, because although you don't need to know math to be a good developer, it certainly does help to reason logically about things. So in this video, I'm going to explain to you what a Poisson distribution is. The Poisson distribution is incredibly versatile. Let's say you want to compute the number of mutations in a DNA strand after exposure to radiation. Or you want to find the number of bacteria in a small sample of water, the number of radioactive decay events from a substance in a given minute, or the number of photons hitting a detector in a particle physics experiment. This is where the Poisson distribution shines. Now, as always, in order to start to understand a new concept, you want to begin with a concrete definition. At its core, the Poisson distribution is a discrete probability distribution. Discrete just means that it deals with outcomes that are countable rather than measurable on a continuous scale like height or weight. Specifically, it helps us answer the following question. What is the probability of a given number of events happening in a fixed interval of time or space if these events occur with a known constant average rate and independently of the time since the last event? You can think of it as the go-to tool for modeling the occurrence of relatively rare events over a specified duration or area. But to understand when to use the Poisson distribution, you have to consider a couple key components. First are events. These are the occurrences of what you're counting. For example, a customer arriving, a machine failing, or a typo on a page. Next is the interval. This is a fixed and well-defined period of time, for example, an hour, day, or month, or a region of space, for example, a square meter, a liter of liquid, or a page of text. And then there's this Greek letter lambda, which is the known constant average rate. You need to know or be able to estimate the average number of times an event occurs within that specific interval. It's important to note that this rate is assumed to be constant throughout the interval. And next, you have independence. The occurrence of one event must not affect the probability of another event occurring. For example, a customer arriving now shouldn't make another customer more or less likely to arrive in the next minute. And the final concept is non-simultaneous events. Two events cannot occur at precisely the same instant. There's always some, however small, time or space separating them. The magic of the Poisson distribution lies in its formula, known as the probability mass function, or PMF. So essentially, it answers the question, if events happen randomly at a certain average rate, what is the likelihood of observing exactly k of these events within a defined window? Its core function is to quantify the randomness associated with events that occur independently and at a constant average rate. By calculating these probabilities, we can predict the likelihood of different event counts. For example, determine how probable it is to observe 0, 1, or 2, or any other number of events. Understand the variability around the average, so we can see how much the actual number of events might deviate from the expected average rate. As boring as it may sound, based on the probabilities, we can assess risks, plan resources, or evaluate the significance of observed event counts. If you are interested in taking your software engineering skills to the next level, I would encourage you to that teach building Git from scratch, building an in-memory Redis database, an HTTP web server. You can find a link in the description down below as well as the pinned comment. So here is the formula, perhaps a bit scary looking. This is the probability we want to calculate. The probability that the random variable x, which represents the number of events, is equal to a specific count k. K is the number of occurrences of the event you're interested in. It's a non-negative integer. For example, what's the probability of exactly 3 calls? Here we can set k equals 3. Lambda is the average rate of event occurrences within the given interval. It's the core of the distribution and the only parameter. For example, if a call center receives an average of 10 calls per hour, then lambda equals 10 for that 1 hour interval. E is Euler's number, which is a fundamental mathematical constant approximately equal to 2.71828. It appears naturally in processes involving continuous growth or decay. And k factorial is the product of all positive integers up to k. For example, 5 factorial is 5 times 4 times 3 times 2 times 1, or 120. And for k equals 0, 0 factorial is defined as 1. The mean, or mu, is the average or expected number of events in an interval, and it is simply equal to lambda. The variance, or sigma squared, measures the spread or dispersion of the data around the mean. For the Poisson distribution, the variance is also equal to lambda. So the variance is the spread around the mean. It tells us how much the actual number of events we observe in different intervals tends to deviate from this average.
in this video, I'm going to be explaining interpolation, and I'm going to do that with this frequency distribution table. But before I can do that, I have to get this filled out a little bit more. I need to have my cumulative frequencies and my cumulative percentages. I was going to do that before I started into the video, just to have
Hi, this is Mario with Mario's Math Tutoring. In this video, we're going to talk about the difference between interpolation and extrapolation. So let's get right into this video. So you can see I've got a lot going on here on the whiteboard right now, and that's because this video is a continuation of the video I did talking about how to find the equation of the line of best fit and how to approximate that line, and then you write an equation for it. But continuing on here, we're talking about what's the difference between interpolation and extrapolation. Well, once you find that equation of the line of best fit, okay, which is this one right here, y equals 4/3 x minus 13/3, you might want to use that equation to make a prediction. You might say, well, I wonder if I was to, pick a value, say for example, like when x is 2, what would be the y value? We don't actually have a data point here where x equals 2. We could go down to that line of best fit and approximate it and say, look, looks like maybe negative 1.5, and then go ahead and use our equation to find out what that y value is. Now that's called interpolation because what you're doing is you're picking a data point that's in between some of the actual data points that you got from your experiment or your study. Now if you wanted to find out a point that was way out over here or way out over here, okay, that's kind of beyond what you took your data points for, that's called extrapolation. So for example, if I wanted to find out, well, what's y when x is like a -5 over here? Well, I could approximate, I could go down and say, well, if I extend this line, it would be somewhere over here, that's the y value. Or I could use the equation and put in that x value and find the y value. That's called extrapolation. Now which one of those do you think would be more accurate? Well, if you said interpolation, you're right, because we know the basic trend. Okay, we know it's trending up to the right. We have an approximation of the rate at which it's increasing. And so if we pick a point that's in between some of these known data points, it's going to be probably pretty close to what this line is approximating. However, with extrapolation, say for example we pick a point way out here, it's possible that the graph all of a sudden could level off, or maybe even go down. Right? We don't know what's going to happen way out on the extremes beyond extrapolation beyond, and it's possible that it could continue up at this rate, and we could use our line of best fit to find that data point. But again, just to clarify, what's the difference between interpolation and extrapolation? Interpolation, think in between, and extrapolation, think beyond, either beyond the data points to the right or to the left. So I hope this helped you understand interpolation and extrapolation better. Subscribe to the channel, check out more math videos on Mario's Math Tutor YouTube channel, and I look forward to seeing you in the future videos. I'll talk to you soon.
In this video and the next two videos, I want to talk about the numerical problem of interpolation. In interpolation, you are given a set of points. So let's say x0, y0, x1, y1. So let's say n plus 1 points, so xn, yn. These are given, so that means they're supposed to be in exact values. So the y, say, is some underlying function of x, and you know the value of the function at these n plus 1 values of x. The problem of interpolation is that given some other value of x that is not on this list of x0 through xn, what is the value of y at that other value of x? So you're interpolating, that's what we say. There's three main types of numerical interpolation.
going on, guys? John Elder here from Codemy.com. In this video, we'll look at tensors and PyTorch for deep learning. Like I said, in this video, we're going to look at tensors. But before we get started, if you like this video and want to see more like it, be sure to smash the like button below, subscribe to the channel, give me a thumbs up for the YouTube algorithm, and check out Codemy.com, where I have dozens of courses with thousands of videos to teach you code. Use coupon code YouTube50 to get 50% off lifetime membership. All my courses, videos, and books for one small fee, which is insanely cheap. All right, moving right along in our PyTorch for deep learning playlist. In this video, I want to start to talk about tensors. Now, we're not going to dive super deep into this because I would rather just kind of move forward and start using them. But you need to have some basic understanding of what a tensor is, what it's all about, some basic stuff about it, and that's what we're going to look at in this video. So, what is a tensor? Well, a tensor is very much like a NumPy array or a Python list. It's just the next progression of that thing. So, you have a Python list, it holds data, it works okay. If you're going to start to use machine learning, you use NumPy arrays. They're just like lists, only they're more powerful. You can do more stuff, they work faster. When you get into deep learning, you start to use tensors, which are very much like NumPy arrays, but are again more powerful. They allow us to do all kinds of different things, and they're more suited for GPU use, so we can use them using GPUs to do faster stuff. So in PyTorch, a tensor is a torch.tensor, and it's a multi-dimensional matrix containing elements of a single data type. It doesn't have to be, it can be a scalar, it can have one, one level, it doesn't have to have multi-dimensions, but they generally have multi-dimensions, and it's just a big matrix, right? It's very similar to a NumPy array, but full of fun things that make them work better on GPUs versus regular CPUs. The default data type is float of 32. Now, default data type in NumPy is a float 64, I believe, so it's a little different there. You can change it into 64, float 64, or anything else you want, really, and we'll get into that in the future, but the default is float 32, so keep that in mind. And of course, it is more suitable for deep learning than a NumPy array. So I've got my Google Colab open, and I've got a file I'm calling it tensors, and as always, you can find a link to the code in the pinned comment section below, as well as link to the playlist with all the other videos in the series. So check that out if you haven't so far. So let's just kind of walk through this from the very beginning, so you have a very basic understanding of what these things are. So right away, I'm importing Torch. We always want to import Torch, and I'm also going to import NumPy as NP, so we can play around with NumPy arrays a little bit just to see. But what I really want to do is start out just very basic with a Python list, so you can really connect the dots and not be overwhelmed by what a tensor is, because it can get overwhelming if you really dive into it, because there's so much stuff you can do with these tensors. But I just want to make it very easy in this video. So let's just create a list, right? My list. And in Python, you do that just with square brackets, and you just put stuff in it, right? And that's a list. Now we can print this out. It's my underscore list, and boom, there it is. So that's just a basic array, one dimension array. Now, of course, we can have a multi-dimension array if we want, multi-dimensional, whatever you want to call it. And here's 6, 7, 8, 9, 10, whatever. We print this out, right? Multi-dimensional array. Very basic, very easy to understand. You can have all kinds of stuff in here. You can have numbers, you can have letters, you can have other arrays, you can have all kinds of different data types of things inside of here. Well, okay, that's your basic Python list. We all understand what that is if you have any Python experience whatsoever. Very basic, very simple. A NumPy array is really not much more complicated. Before we get into NumPy arrays, I've got an entire YouTube playlist on NumPy arrays if you want to deep dive into them again. If you want to dive into this, but there's like you guys. So just go np.random.rand. And let's say we want a 3x4. What's this going to look like? So let's just print out this np1. And we get this array. It's of a data type array, right? NP array, actually. And we have 1, 2, 3, 4 columns and 1, 2, 3 rows, right? And if we want to play around with this, we can np1.dtype just to see what kind of data type this is. And it's a float 64, right? Like I said, the default data type of NumPy arrays is float 64. So, okay, just basic NumPy array, you understand that. This is very similar to this Python list, right? If we just pulled in a 3 here, this is going to look very similar to just a regular Python list, right? So again, list, a little bit more powerful. NumPy array, a little bit more powerful. Tensor, right? So to create a tensor, I'm just going to call this tensor underscore, I don't know, let's call this a 2D one. We just call torch dot, let's just create a random one. And same thing, let's go 3, 4, just like our NumPy array. And if we want to take a look at this, tensor underscore 2D, you can see right here it says tensor, up here it says an array. So this is a NumPy array, this is an actual tensor, it's its own thing, right? And again, 1, 2, 3, 4 columns and 1, 2, 3 rows. So if we kind of look at both of these, this guy and this guy,
Yes, you can.
we learned how to avoid aliasing when downsampling images. The key tool was convolutions. But how about non-factor of 2 resizing, or rotations, or other types of transformations, or making images bigger rather than smaller? All of these problems require the same basic tool, interpolation. And it turns out that convolution can solve this too. Let's start in 1D. 1D convolution is just like 2D. You slide a kernel of weights across a function. Here's the kernel, and the function we want to filter. This is a mean filter. It has a weight of 1/3 for each sample. And when we multiply these weights with the sample values and sum them up, it computes the average. Now we slide the kernel to the right and compute the next output sample. Got it? Now let's try a different filter shape. And we'll connect the dots to make it continuous. If we apply the filter as before, we generate the original sample point. But now let's try applying this filter between sample points. Again, we do this by multiplying the filter values times the blue samples. That interpolates a point right between them. And when you move a little, it will compute another point on the line between the 2 samples. And if you slide this filter continuously along the x-axis, it will draw the line connecting the 2 samples. This is cool. It's a connect the dots filter. Now let's try a more interesting example. It works. We can interpolate any value between the samples. But what if we want a smoother curved reconstruction? Maybe we can try using the Gaussian kernel instead, like this. This does produce a nice curved reconstruction. But the red curve doesn't interpolate, meaning pass through the blue points. Why not? Well, the Gaussian is computing a weighted average of each sample with its neighbors. And you can see that this usually won't pass through the sample points. So how do we fix this? If we want to reconstruct the red point here, we'll need our kernel to have a value of 1 here, and 0 for all the other sample points. Our hat function satisfies these constraints, but we want a smoother result. A narrow scaled Gaussian also works. But it produces this very sad droopy interpolation. The problem is that the area under the curve is less than 1. And this causes the reconstruction to lose mass between the grid points. Well, how about if we have something Gaussianish in the middle, and sinish on the sides? This could work, but we need the area under the curve to sum to 1. So let's make the function decay with distance. Here's our sine curve. We want it to decay as you move to the right. An easy way to do this is to divide by x, the distance from the origin. That does the trick. We'll introduce a couple pi's to align with our grid. We've derived the sinc filter, an elegant mathematical formula that satisfies all of these constraints. And the sinc even produces that nice Gaussianish lobe in the center too. If you convolve the sinc filter with these samples, it produces this beautiful curvy result. How does it work on this boxy function? Well, not so well. It creates wiggles where things are supposed to be straight. This phenomenon is called ringing. In 2D, it looks like this. Yikes. Let's see what's going on here. Our box reconstruction looks suspiciously like this function. Remember from the Fourier transform video? It's a sum of sinusoids. And if we keep adding more sines, it eventually converges to the box. As we saw in the Fourier transform video, sinc is a low-pass filter, and it eliminates the high frequencies of the box. But this reconstruction is not very box-like. Too many wiggles. Sinc is just not good with sharp edges. So a lot of smart people have worked to design filters that try to give you the best of both worlds. Good reconstructions of both curvy and straight objects. 2 popular ones are cubic and Lanczos. These are basically truncated versions of sinc. On the box function, Lanczos does slightly better than sinc.
Well, we covered bilinear interpolation and nearest neighbor interpolation, which obviously see a lot of use in any kind of imagery sampling. But of course, the one we all use now is bicubic, and I kind of left that one hanging, so let's talk about how that works. Thinking back to where we were before, we're looking at some pixel side on, and what we're doing really is trying to find some values in between where the pixels are, right? Because if we're resizing an image or we're moving an image, the new locations we've got won't necessarily match up with the previous ones. So if this is our image here, so these are my 4 actual pixels. Nearest neighbor will just sample between these pixels depending on which one's nearest. So it'll sort of go along like this, and then it'll go like this, like that, okay? Which is why you get these sort of square pixelated edges of nearest neighbor. That's very fast to do that. And as I said last time, we haven't made up any data doing that. This is our sample, this stretches to here in some ways, so you know that's good. Bilinear takes literally a linear interpolation between these points. So it'll be like this, and then this, and then this. Right? And then maybe it'll go off in this direction depending on what the other pixels are. Now this works fine sometimes, right? But if we've got step changes, or weird areas of contrast changes, and funny shapes, so maybe this goes up and then down suddenly, this starts to look not very smooth.
Hey everyone, in this video I'm going to be going through linear interpolation and how to derive the equation for linear interpolation. This is a useful equation to use when you have values of data at discrete data points and you'd like to interpolate between the two to get a value at an unknown point where the data wasn't taken. So for instance, if you have properties at certain temperatures and you want to get the property at a temperature that you didn't actually measure or there's not data for, you can linear interpolate to get that temperature. So to start out, we have just 2 points in this xy plane. This is point 1, this is point 2, so point 1 in green, point 2 in blue. And point 1 has x coordinate x1, y coordinate y1, point 2 has x coordinate x2, y coordinate y2. And the problem is, what happens if I want to get a data point, the value of y, at some x location, x in red? And so the way that we can do that is to linearly interpolate between these 2 data points. I'm going to draw a straight line between the 2 known data points. And we're going to assume that we know x. So for instance, let's just say we have a density of some material at a temperature here and a temperature here. And now I say, okay, well I want the density at this temperature here. So what this means is we can draw a point on this line between the 2 points. And this will be the resulting y value. We can get this y value from, well, I'll show you next, based off of knowing these 2, and then this is your input, and then these 2 y points as well. So for a straight line, you know that the slope of the straight line is the change in y over the change in x, or you can call it the rise over the run. And in this case, for the blue and green points, it is y2 minus y1, that's a change in the y direction, x2 minus x1 is a change in the x direction. And along this line, since it's linear, we know that there's a constant slope, which means that for this point here, the slope between this red point and the green point has to be the same as the slope between the blue point and the green point. So that's what this is showing here, is that we start out with the original slope from before, and we just say it's equal to the slope between the red and the green, so that's going to be y minus y1 over x minus x1, and I can drop this perpendicular down there. Okay, and just rearranging this, right, the only unknown that we have right now is y, because we're saying, oh, I want it at a certain x value. And so if we rearrange this by just multiplying the denominator over to the other side, we get y minus y1 is equal to this thing times the denominator here. And we're just solving for y. The only unknown, and we solve for y. And we get this equation here, which makes sense because we are essentially saying we're going to start at this y1. We're trying to get to this y position. We're going to start at this initial y, and we say how far do we need to go in the vertical direction to get to the new y, and that depends on the slope and how far you went. So this term here is the slope of this line, and then from that slope, if we multiply it by this x minus x1, that's this distance here, we'll be able to get to the new y location. Now we can do a quick example. This one's straight out of the thermodynamics book that I have from the property tables for temperature. This is for air, temperature, and specific heat at constant pressure. And so the knowns that we have in the book, they're given at 250 and 300 Kelvin. And so at 250 Kelvin, we know that the specific heat at constant pressure is 1003 joules per kilogram Kelvin, and at 300 it's 1005 joules per kilogram Kelvin. And so here's the equation written again. So you can see that this is our known 0.2, known 0.1. We're trying to find, I'll try to find both of these, 225 and 280. And so I've relabeled here, this is still the x-axis, but it's temperature now, y-axis is the specific heat. You can see our two
Go end-to-end from raw data in a database to a deployed model with a monitored API endpoint using multiple core data robot capabilities along the way.
We'll be making predictions with our Vertex AI model. Hello everyone. In today's tutorial, we'll be making a predictions with our Vertex AI model. There are two options to do this. First is batch prediction. This is for processing accumulated data when you don't need immediate results. Second option